So welcome to the 50th Theoretical Physics Colloquium by Professor Keith Olive from William Fine Theoretical Physics Institute and Minnesota Institute for Astrophysics at the University of Minnesota. He received his PhD from the University of Chicago in 1981. He had several postdoctoral positions, including one at Harvard Smithsonian Center for Astrophysics at Harvard University, at Fermi National Lab, and at CERN as a scientific associate, and everything until 85 or so. Then he received a faculty position at the University of Minnesota. He became a distinguished McKnight University professor at Theoretical Physics Institute in 1998. Between 1999 and 2005, and then between 2013 and 2019, he was the director of Theoretical Physics Institute at the University of Minnesota. Since 2020, he is the Gloria Becker-Lupkin Chair of Theoretical Physics at William Fine Theoretical Physics Institute. He received numerous awards and honors over the years, including Fanny and John Hertz Foundational Fellowship, NATO NSF postdoctoral fellowship in 1982, Presidential Young Investigator Award in 1987. He received George Taylor Research Award in 1988. He became the Fellow of the American Physical Society in 2003. And in 2018, he received Hans Bether Prize from American Physical Society. He is also a member of the Particle Data Group. His research interests include particle physics and cosmology. He worked on many topics in Big Bang nucleosynthesis, Big Bang baryogenesis, inflation, particle dark matter, and many, many other topics. And today he will be talking about Big Bang nucleosynthesis post-Planck. And with that, I'll give the microphone to Keith.
Okay, well, thank you, Igor. Let's see if I can get this in good shape. And annotate, spotlight. And so it should be okay, I think.
Yes.
Good. Well, I can still say good morning. I'm not sure it's morning for everybody when this is virtual, but so I'll be talking about sort of the recent status of Big Bang nucleosynthesis, in particular, what we know about nucleosynthesis in the post-Planck era. So I'll tell you a little bit about just BBN in general and how the CMB is used to primarily to determine the baryon density, which is the real key input for Big Bang nucleosynthesis. I'll talk a little bit about the observations, deuterium, helium-4, and lithium-7. And then I'll get to the impact. There have been some new cross-section measurements, which are quite important. And I'll tell you a little bit about the impact of those and what we actually hope for in the future. And I'll also talk a little bit about the impact on determining the number of neutrino degrees of freedom, particle degrees of freedom, and how you can use that for constraints on beyond the standard model physics. And I'll talk a little bit about the future, which would come from primarily from CMBS4. So let me start. Oh, why I have this is on my screen still. I don't. Okay, so all of you can see, it's all right what you see. You just see the slide and that's it? Okay, because I still have this. Oh, I can close it. Let's see if I can try and close it. There, that's a little bit better already. Okay.
Well,
So BBN started, these are the three principal players for the onset of BBN, George Gamow, Ralph Alpher, and Robert Herman. really, you can even say just the Big Bang Theory as we know it, as we describe the Big Bang Theory today. These are the people that are primarily responsible. Often it's a little bit different, this set of people, and now I'm not able to. Okay, so something happened. Okay. The three that normally get associated with Big Bang, or often I should say associated with Big Bang nucleosynthesis or Big Bang theory, is alpha, beta, and gamma. And you can see the obvious humor in the three authors. This is the paper that the three of them wrote together. There's a little story behind this paper. So I had the opportunity when I was a graduate student. Hans Bethe actually came to give a colloquium. I believe it was a colloquium at the University of Chicago. And so he was asked about this paper. And he was very frank about it. He said that, he really had nothing to do with the paper. He said that this was Gamoff's sense of humor, that Gamoff was working on this with his student Alpha, and they thought, well, Alpha and Gamoff, okay, it would be sort of nice to have Beta in there. So they sent him a copy of the paper, and in Beta's words, he said, I read the paper, I didn't see anything obviously wrong with it, so I agreed to be part of it. What they tried to do is to explain the abundance, abundances of the elements. And really what they were trying to do is explain the abundances of all the elements. And they weren't very successful in that. Sort of a modern picture of that, maybe a little bit cleaner, is here. And now we know, of course, that the Big Bang nucleosynthesis, or the Big Bang, is really responsible only for the very left part of this figure. That is, well, you start with hydrogen, if you want, protons, and you're making helium, a lot of helium, and then you make a little bit of lithium and basically nothing else. So the rest of the table of elements and their abundances is really all coming from stellar type processes or cosmic ray nucleosynthesis. I'll give you a little bit of a historical perspective on this and the connection with the microwave background. It's a very simple argument in how you can get the right temperature for the CMB using the arguments for Big Bang nucleosynthesis. So they knew at the time that the conditions that you needed to have nuclear reactions taking place is that you needed to have a temperature of above about 100 keV. I'm just going to use very round numbers here. So 100 keV temperature, and if you want, can call it Gamoff's theory, 100 keV temperature correspond to an age of the universe less than about 200 seconds. Okay, so you only had about that 200 seconds to do anything. And they knew the cross section, the first link, if you want, in the chain would be proton plus neutron going to deuterium and a photon, so photoproduction of deuterium. That cross section is about 5 × 10⁻20 centimeters cubed per second. And then you can then determine what baryon density you would need given that cross section and that time scale. And that's about 10⁻17 per cubic centimeter. So actually not that dense if you think about it, right? If you also know something about the baryon density today, and just again, very rough number, 10⁻⁷ per cubic centimeters, and then you know that the baryon density scales is 1 over the scale factor cubed or the temperature cubed, that's enough to already predict the microwave background temperature today. And just with these numbers, you would get 10 degrees, okay? So that's, now I show this paper, this is by Alpha and Herman. Actually, Gamoff's not even on this paper. And what they did is they said, this is basically the same argument. This is where the argument on the previous slide comes from. They said, okay, if we know that the baryon density, rho m, and rho r, the radiation density at the time of nucleosynthesis, the radiation density is, that's the temperature, that's the 200 keV that I said, or 100 keV that I said. And if you know something about the matter density today, then you can get the radiation density. And I always like seeing this where they say, which is the least well-known quantity. Of course, today, the radiation density is probably the best known quantity of anything in cosmology. It's just the temperature of the microwave background, which we know to very, very high precision after COBE. So using that, they were able to get what the temperature was, and they did a little bit better than I did on the last slide. They say it's 5 degrees. Okay. But they still even did better than that, because they said, well, you know, there's still some uncertainty in these quantities. And if we fold in some of these uncertainties, it could be as low as 1. So basically, they were saying in 1948 that the temperature of the microwave background was between 1 and 5 degrees. Okay, that's not so bad given that it's 2.7 today. Okay, so to me, this is really remarkable work, some of the earliest work in Big Bang cosmology and nucleosynthesis, with really fantastic testable results that were borne out. Of course, microwave background now is known to much, much higher precision. Baryon density, this is from most recent Planck results. Baryon density, I'll probably be flipping a little bit between the omega b h squared. Omega b is the ratio of the baryon density to the critical density needed to close the universe, and h is the scaled Hubble parameter in units of 100 kilometers per second per megaparsec. And so you see quite high precision. That's effectively equivalent to a baryon to photon ratio, which is eta, and then in units of 10 to the minus 10, that value of eta is 6.12 times 10 to the minus 10. And then you see the accuracy from the anisotropy spectrum is really quite remarkable. The curve there, of course, you know, is not a fit, is a theory curve. So the conditions in the early universe for nucleosynthesis, we start with temperatures above an MeV, we have equilibrium. The radiation density now includes not only photons, which is the 2 in that second line. I guess I can use, oh, my pointer disappeared. Okay.
That's when you close that window that was obstructing your view.
Oh, okay, but now I can't get it back. Okay, it doesn't matter. Yeah, I see. All right. So the radiation density, the 2 is for photons, the 7/2 is electrons, positrons, and then normally in the standard model, n nu would be 3, but okay, whatever the number of neutrino flavors is, that would contribute to the relativistic number of degrees of freedom. And then, as I said, eta is the baryon to photon ratio. So in equilibrium, and in particular, what we're interested in here is beta equilibrium. So equilibrium between neutrons and protons, and there you have the beta reactions exchanging neutrons to protons. These interactions will freeze out at about an MeV, roughly, when the expansion rate of the universe, which in a radiation-dominated universe goes as the Hubble parameter, which is t squared over n Planck, so it's the square root of rho. And you want to compare that with the interaction rate, which you know is going to go as g Fermi squared, and by dimensional grounds, it'll be g Fermi squared times t to the 5th. So as the universe cools, eventually the reaction rate becomes slower than the expansion rate, and those reactions effectively stop. That is, the mean time between reactions now takes longer than the age of the universe. And at an MeV, you can compute, it's a little bit less than an MeV, you can compute the ratio of neutrons to protons from their equilibrium value. That's at about a 1/6, but nucleosynthesis doesn't start right away, and some of those neutrons decay, and you go from about a 1/6 to a 1/7. Again, very rough numbers. Now, nucleosynthesis is delayed primarily because of the number of photons present in the radiation background. So you can look at the production of deuterium, and then you can look at the photodestruction of deuterium and compare the two. The production rate goes as NB sigma, and the destruction rate goes as N gamma sigma modulo a Boltzmann suppression factor if you're at a temperature below the binding energy of deuterium. But remember, there are 10 to the 10 times more photons than there are baryons. So nucleosynthesis can't really start. That is, you can't get deuterium to stick around until the temperature drops to about 1/10 of an MeV, which is a factor of about 20 below the binding energy of deuterium. Okay. Then if you make the approximation that all the neutrons that are left over end up in helium-4, and you plug into this very simple formula 1/7, you would say that you'd have 25% of the mass density in baryons in the form of helium-4. And then the rest of it gets scattered between deuterium and helium-3 at the level of about 10 to the minus 5, and lithium at about 10 to the minus 10 by number. So once things start, so as I said, you're going to start by making deuterium. And here you have all of the various reactions that will start flowing once the deuterium is present. And you can see a lot of the arrows are pointing towards helium-4. It's like all roads point to Rome. You get a lot of helium-4. There's a mass gap at A equals 5. There are no stable nuclei at A equals 5. There is helium-5, but it's highly unstable, particularly on the time scales that we're talking about, which are seconds or minutes in the early universe. You can, in principle, make some lithium-6, and you have lithium-7 there. Actually, what you make mostly in the Big Bang is beryllium-7, which much later beta decays to lithium-7. There's another mass gap at 8, and even though again, boron-8 and lithium-8 are shown as looking like stable elements, they're stable on laboratory timescales, but they're not stable on Big Bang timescales. So there's another gap. And by this time, this all takes a little bit of time. And by this time, the temperature is cooled. It's harder to make the nuclear reactions occur. You have bigger and bigger Coulomb barriers to overcome. That's basically it. You make some, as I said, some beryllium-7, and there's really not much else that you can do. So the inputs, the previous figure had a lot of nuclear reactions in it. The code that we use goes, I think, out to aluminum. All these things are sort of irrelevant. There are 12 principal reactions that really govern the final abundances of the elements, and those are the ones shown here. They show some of the cross sections just to show you that some are very well measured and some are not particularly well measured. I'll talk a little bit more about the first reaction on the left, the dp gamma reaction, which is labeled B. So it's the lower left of the figures, where you see there's just not a lot of measurements that were present, and that was recently done just in the last few months, some new data on that. And I'll talk about that a little bit later. So, as you're probably aware, Big Bang nucleosynthesis could not explain the abundances of all the elements. And so people sort of lost a little bit of interest in the early 50s, I would say, and that led to the growth of stellar nucleosynthesis, which of course is a very important subject in its own. And that's what leads to the explanation of the bulk of the elements. But still some hanging questions, and that's, where does the helium-4 come from? I said there's 25% by mass. Stars make some helium-4, but it'd be very difficult to imagine a situation where you can get enough stellar activity to convert 25% into helium-4. The other problem is deuterium. Since deuterium is observed in nature, where does it come from? It can't come from stars, because in the pre-solar pre-main sequence phase of stars, any deuterium that's present actually gets burned. So stars actually are destroyers of deuterium, not producers of deuterium. And so if there is any deuterium around, that should all come from the Big Bang. And so then somewhat later, in the late 50s and then certainly into the 60s and 70s, nucleosynthesis became much more interesting, but certainly just focused on the very lightest element isotopes. So this is what you get out of nucleosynthesis. Here, I'm showing a plot as a function of the baryon to photon ratio from 10 to the minus 10 to 10 to the minus 9. Helium is plotted as by mass, and then the other three are plotted by number relative to hydrogen. And you see quite clearly that the abundance of helium-4 is about 25%, okay, with some spread of about 1% depending on the baryon to photon ratio. And the deuterium and helium-3 abundances are down, level 10 to the minus 4, 10 to the minus 5, and lithium is way down between 10 to the minus 10 and 10 to the minus 9. In the standard model, if you assume 3 neutrino flavors, now the neutron mean life, which also has an effect on the abundance, particularly for helium-4, is quite well measured. I'll say a little bit more about that later. Baryon to photon ratio in principle then is really the only input that you need to worry about. And even there, it's not an input anymore because the CMB determines the baryon density. So in principle, nucleosynthesis is a parameter-free theory. You just read off the predictions. You have predictions for all the light elements. There are some uncertainties. Here I'm showing what the uncertainties. The biggest is lithium-7, the relative uncertainty. And you see there's almost no uncertainty in helium-4. What's plotted there is actually 10 times the real uncertainty, just so that you could see it off the axis, off the bottom axis. So, and that's mainly coming from the neutron mean life uncertainty. So helium-4, the prediction for helium-4 is quite robust. And I'll talk a little bit about, you'll see that deuterium uncertainty based how that changed with the new cross-section measurements. Let me talk a little bit about the observations. Helium-4 is observed in extragalactic H2 regions. These are regions in other galaxies of ionized hydrogen. So those are coming from emission line spectra. Lithium-7 is observed in the atmosphere of stars in our own galaxy, dwarf halo stars, so small stars, long-lived stars, and that abundance is about 10 to the minus 10. Deuterium is the abundances that we get, that we associate with the primordial abundance, is coming from quasar absorption systems. So these are gas clouds that are sitting between us and high redshift quasars. So these are things that are at redshift of about 3. And the light from the quasar comes in through these gas clouds. Some of it gets absorbed. And from that, you can determine the abundance of deuterium. Helium-3, there's no good primordial measurement of helium-3. So there is helium-3 observations, but there's no good way to attach that to a primordial number, as helium-3 is both produced and destroyed in stars. You need to think that you understand the chemical evolution in the galaxy from the Big Bang to today to be able to use that. So I won't say too much more about helium-3. So deuterium, all of it's primordial, as I said. There are other observations outside of quasar absorption systems, but they carry larger uncertainties. So it's observed in the ISM, and you can get its abundance from meteoritic samples or molecular hydrogen in Jupiter. But really, the good numbers are coming from the quasar absorption system. Here's a set of tables taken from Cook et al. This is log of the deuterium abundance. Oh, my little thing came back, but I can't now choose it. Oh, okay. The deuterium abundance here is in the last column, shown as the log of the deuterium abundance by number. What you see here are also the redshift and the hydrogen column density, and more importantly is the oxygen abundance. In the bracket there, that's the log of the oxygen abundance relative to the solar oxygen abundance. So these are all metal poor objects. And as I said, these are coming from quasar absorption spectra. Here's a blow up of one of those. And what you're looking for is the little tail that's coming from the isotopic shift in the absorption feature from deuterium as opposed to hydrogen. This was the situation several years ago. It was all about the right number, the log of the deuterium abundance, but there was quite a lot of scatter that really shouldn't have been there. So it wasn't clear whether this was from observation or if there was something going on in deuterium destruction. But that situation has changed quite dramatically over the last several years with these high precision measurements by Cook et al. And other groups that have been contributed. There's about 11 or 12 measurements now. And you see that's the mean of that. And so the observational average is about 2.55 times 10 to the minus 5, very small uncertainty, 0.03 times 10 to the minus 5. And that's to be compared with the prediction from BBN, which I'll talk more about, is 2.51 times 10 to the minus 5, and with a bigger uncertainty, bigger than the experimental uncertainty. So that's this is the same plot now with the mean of the deuterium abundance shown as that horizontal line. And if I combine that with the abundance, the baryon density from the CMB, you get fantastic agreement. I mean, these three lines are all meeting at the same point. That is, if you use the CMB baryon density to get the deuterium abundance, it agrees perfectly well with the observed deuterium abundance. Let me move to helium. So again, helium-4 is predominantly primordial. So here's a number of data. This is on some ridiculous scale from 0 to 1, but it's there to show you the point that it goes towards an intercept, which is would be the primordial abundance. So if you get high quality measurements of the helium abundance and you can extrapolate it down to, say, 0 oxygen or 0 metallicity in general, then you would know what the primordial abundance was. This is very different from other elements. So if I looked at, say, nitrogen versus oxygen, same data actually, now showing nitrogen instead, all of the elements would go towards the origin. That is, if you go to 0 oxygen or 0 metallicity tracer, the abundance of that element that you're looking at would also go to 0. And that's characteristic of what you would expect in stars, because the stars are making the oxygen, the stars are making the nitrogen. If you take away the stars, you take away both the nitrogen and the oxygen. And that's just not true with helium or lithium. Those are the two that, and deuterium actually. So I said it's coming from emission lines coming from extragalactic H2 region. There are a number of these lines that are observed. You need both helium and hydrogen lines to understand well the parameters of the H2 region that you're looking at. I won't go into a lot of detail of how this is done, but there are a number of parameters associated with these H2 regions. Well, their temperature, their electron density, optical depth, parameters that control the reddening of the light, underlying absorption, collisional effects. And we've moved to, it used to be you take a few helium lines and you would try and get the same abundance to account for 3 or 4 helium lines, and that would be your abundance. Modern techniques do a whole lot better than that, and now we're using Markov chain Monte Carlos to determine all of the parameters self-consistently, including the helium abundance, with the existing data. Now, some of the data is just not very good. You see on the left, you get a very poor constraint on the helium abundance, and you see the chi-squared there is terrible. It's about 20, and you have 9 or 10 observables with 8 parameters. You should never get 20. So it's not clear what's wrong with that data or what's wrong with the model. But in some cases, you get very good, the data gives you a very good fit, like the one on the right. You get a very well-determined helium abundance and a very low chi-squared. So you can use this to select out the data which makes some sense. There have been a lot of improvements. Atomic emissivities have been improved. And then using that to actually get what the convert from the line fluxes to abundances. Adding new helium lines. There was an infrared line added in 2015, first proposed by Izotov, Tuan, and Gusevev. That gave us 10 lines for 8 parameters. We've now just this last year proposed adding a number of additional helium lines and hydrogen lines, so that we get actually 21 observables for 9 parameters. And we've done that for 1 observation so far. So this is again from just this past year, 2021, for a dwarf galaxy in the local group called Leo P. On the left, you see the fits from the old set of lines, that is 9 lines relative to the current situation with 21 lines. And you don't have to go through all these numbers, but the main thing is that a lot of these parameters now are much better determined. The uncertainties in these parameters for example, the electron density, the uncertainty is dramatically is reduced, and has a big effect on the uncertainty in the abundance. At the bottom line, you see the abundance of helium-4 in this object. The uncertainty is dropped by a factor of about 3. And so this is the set of data that we feel you can use to extract the helium abundance. Again, it gives you about 24.5%. The uncertainty just from this one object lowered the abundance from 0.004 to 0.0034. So, and that's with just one object. So we're hoping that new observations will lead to better determined helium abundances. There was just also this last year another analysis using SDSS data on helium. So that's mostly these blue points. They apply the same method that we've been advocating to this SDSS data, and they get smaller uncertainty. It's perfectly consistent with what we had, but smaller uncertainty. And this is probably fine. We've generally argued against taking more high metallicity data, that we want to concentrate on low metallicity data. If we're doing a linear extrapolation, you want to start worrying about whether or not it really is linear out to much higher oxygen abundances. But probably this is fine. Word on the neutron mean life, that's really improved over the years. So this is just a plot as function of time. Of course, this is a measurement as a function of time, not neutron mean life as a function of time. But you see that the uncertainty has gotten dramatically smaller. And I won't even comment on, there's still this little bit of discrepancy and controversy over what the true mean life is today. But given for nucleosynthesis purposes, that's really quite small. And on the left, you just see how those changes affect the abundance of helium-4. And here's a little bit of a scatter plot for the neutron mean life, given some uncertainties in the neutron mean life for a given neutron mean life, and what that does for the helium abundance. So we're talking about small deviations at this point now. So helium-4 prediction is about 247. Very, very small uncertainty you see there, and that's because the neutron mean life is well determined. And the data regression, this is using ours, 2453 plus or minus 0034. So again, we get good agreement. Lithium, I'll go a little bit quicker maybe for lithium. There is not good agreement. Lithium, as I said, measured in the halo dwarf stars. And here the bracket lithium is the log of the abundance of lithium by number plus 12. So 10 to the minus 10 is here shows up as plus 2. Okay, and you're seeing here is a function of temperature. So what you're seeing on the left plot is, and this is called the Speed plateau, this flat part that you see on the left. For stars, this is the surface temperature of a star. At those temperatures, you expect the convection zone to be limited so that it doesn't go down deep into the star where the lithium can be destroyed. And so you expect for those surface temperatures that the surface abundance of lithium is representative of the initial lithium abundance, whereas you see at the cooler temperatures, that convection zone is deeper, and some of that lithium is destroyed. On the right, you see a similar plot, but now showing only data with temperatures bigger than 5,500 degrees. Now for the higher metallicity stars, now that bracket over H is again log relative to the solar abundance. So a tenth is -1 here, a tenth solar is -1. For the higher metallicity, you have to go to even higher temperatures. So staying at only higher than 5,500, at the high metallicities, you see a lot of dispersion and destruction. The diamonds are actually only upper limits. And whereas now on the left, you again get that speed plateau, which is the same as what you see on the left figure. Another way of seeing it is here. The primordial values are this cluster of, or supposedly primordial values would be this cluster of points on the left, and then is distinct from the points with lots of dispersion on the right at higher metallicity. Also, you see what you would expect when you combine nucleosynthesis with cosmic ray nucleosynthesis. So there's going to be some lithium production just from alpha-alpha collisions in cosmic rays, producing both lithium-6 and lithium-7. But the trouble is that there's that yellow band sitting on top. That's the BBN prediction. And that seems to be off. So there's a discrepancy. What's the cause of the discrepancy? Well, we've looked at it, lots of things. It's probably not nuclear rates. These also control the solar neutrino flux, and so you have very good agreement there. There have been new measurements of a number of these cross sections, and they also don't have much of an effect. We thought maybe there were some resonant reactions that might have been missing from the code. In particular, the one we were interested in was beryllium-7 plus helium-3 making an excited state of carbon-10. And that was searched for and wasn't seen. So it's unlikely that that's a resolution. Stellar depletion, if you ask me today, I'd say that's probably the answer. Although we've always argued against it because of the lack of dispersion in the data. Plus, there's some lithium-6 observed. There was a little bit of a time where they thought there was a number of stars with lithium-6. Most of that has actually gone away. It's probably really just lithium-7. We thought that it was very hard to get a uniform destruction of lithium if the abundance was 4 or 5 times higher, given that you have different masses, different rotational velocities, different metallicities, different surface gravities, all sorts of things contributing, yet the depletion factor seems to be constant. And there are models that do that. Even more troublesome now is that speed plateau, which I say was now correspond to these points on the right at metallicities around 2, 2.5, minus 2.5. There are more observations at even lower metallicity where it doesn't seem so uniform anymore. There seems to be some dispersion, which would be characteristic of destruction. And here's some data from 2018. Again, at very low metallicities, maybe there is dispersion, and some more data at 2019. So whether or not that value that's seen in this surface abundance of these stars really is primordial or not, I think you could call into question. Of course, it's fun to think of other things. Stellar parameters is still sort of more standard, but and that's been looked at, whether the temperatures are correct, whether the metallicities are correct. It seems very unlikely that playing around with the stellar parameters will do something, but you could go beyond the standard model and talk about decaying particles, axion cooling. You could imagine that the fundamental constants in nature were different at the time of BBN. Problem with all of these things is that the deuterium agrees really quite well. And anything you do to affect lithium probably affects deuterium as well. So by fixing one, you end up messing up the other. So I'm not going to go into any more of that. I'm going to move on now to the analysis of combining the CMB with BBN. There are a number of likelihood functions that you could construct. Simplest, probably just to think about, is just the observations. No BBN, no CMB. You just get some observations. It tells you the likelihood function for a given observation. And those are shown here as yellow distributions for helium, deuterium, much more narrow because the observations are quite good, and for lithium. You could use the CMB alone. So no BBN, no observations, just CMB to determine the helium abundance. So just the presence of helium in the universe at the time of CMB decoupling will affect the CMB anisotropy spectrum. That's the cyan curve, very broad. They don't determine it very well, but you can think it's actually rather amazing that they determine it at all. So, so that's interesting. Now you can start combining CMB and BBN. You have to be a little bit careful with the Planck data and their papers because they actually use a hidden piece of BBN. They connect the helium abundance with the baryon density in the paper, but they tell you they do this, of course. If you go to their raw data, they actually give you the data where they take that out. They actually take out BBN and they just give you their likelihood functions that depend on the baryon density and the helium abundance with no assumptions made. And that's what we're using here. You can convolve that with the BBN code and BBN likelihood distribution, which is also a function of the baryon density. And then you can convolve that and get a distribution which is shown here in purple. And so you can compare that directly with the observations. You see it's very good for helium and deuterium. There's no observations, as I said, for helium-3, and it's not so good for lithium. And these are the central numbers that you would get from the BBN calculations. So we can compare this is just a comparison between our results in 2016 and French group Pitrou et al. From 2018 and our more recent results, which use the latest Planck results from 2018 as well. On the left, you just see the best value for the baryon to photon ratio. This assumes 3 neutrino flavors. Everybody's agreeing on the helium-4 abundance to very high precision. Deuterium is a little bit different. I'll come back to why Pitrou et al. Get a different deuterium abundance. See, this is quite a bit bigger than even the uncertainties that you would expect. Helium-3 is more or less the same. And again, lithium-7 is a little bit different for Pitrou et al. For the same reason. They're basically using different cross-sections, which I'll get to a little bit later. Oh, actually, I'll get to it right now. So Cook et al. And also actually Cook et al., they're actually claiming some kind of discrepancy between the theory and the observations. And this has to do with the fact that they were noting that there wasn't a lot of deuterium cross-section data. And here's this DP gamma cross-section that I mentioned earlier. And there are theoretical arguments you can make done by Marucci, and Cook et al. And Pitrou et al. Do their own as well. But they're basically higher than all the existing data at the time. Even though there wasn't much data, there was some data, but their theoretical theory-based cross-sections were higher. That is more deuterium destruction. You see that here on the right. What they're using what's shown here is normalized cross-section relative to what they were using. That's the horizontal line at 1. And there's some data you see scattered a little bit below. So they're basically using a higher destruction rate, and that's what's accounting for the fact that they have less deuterium coming out. Okay, so I said the Luna collaboration has made new cross-section measurements all across the BBN range. And there you see it here, left and right are the same. It's just one is log, one is linear. It might be easier to see it actually in the linear on the left. And you see the old data, there's not much of it there. And the little red points that sort of going up along the line, along the shaded region, is the new Luna data. The shaded region there is our combination of the Luna data along with all the prior existing data, and it's 1 sigma uncertainty. You see, of course, the new fit is very close to the Luna data because their errors are so much smaller than any of the existing pre-existing data that their result completely dominates the cross-section. And it's in contrast to the Marucci S factor here, which is considerably higher. So this is a lot closer to what we had before. And so this is what we see here. So FOYY was our 2020 result. So post-Planck, the theory result that is from, if you use the Marucci rate, the Luna collaboration did their own fit. So I quote that here. And our current fit, which is almost identical to the Luna. Again, it's not a surprise because we use their rate, but we don't use exclusively their rate, but their rate is so dominant that it's effectively the same thing. And we have a slightly higher uncertainty because there is a little bit of discrepancy in the rates, but it's basically the same thing. So what does that do? Here you see again, just all these are for deuterium, the old result, the new result, the theory result in the upper right, and our result and the Luna result are essentially the same. And here, so this is the same table, a little bit broader. So P-true, they have 2021, they still have a low rate. So it's not just dp gamma. They're also using enhanced rates for DDP and DDN. And I'm not going to say more about that now, but I'll just come back to that as part of a wish list later on. And this is what happened to the uncertainties in the deuterium abundance just with Luna. And you see the uncertainty to deuterium has really improved. And so you can imagine that with additional, so now the residual uncertainty in the deuterium abundance, this is the predicted abundance from BBN, would further improve if we could have measurements of the other two deuterium destruction rates, the DDN and DDP. Okay. So if you use the Planck data, now again, with subtracting out their BBN correlation, this shows the top part is Planck after 2015, the bottom is Planck after 2018. Fortunately, not a lot of change. They did have improved data for somewhat of a change for helium-4. On the left is just a 2-parameter fit, baryon density and helium abundance. On the right, we can add in that maybe the number of neutrino flavors isn't fixed to 3. They give you the likelihood distributions for variable and nu, and so you can have 3-dimensional likelihoods. And this is our fit to their data. This is our analysis of their data. And this is their data. Again, this is the Planck result, CMB only determinations. What looks like a nearly horizontal line, it's actually not horizontal line, is the BBN prediction, and that thickness is a 3 sigma uncertainty. And so you see again the agreement between the helium and the CMB predictions. Now you can start taking these likelihoods and convolve. You can either take the CMB, the likelihood alone. That one is the red dot dash. That will determine for you quite well with 3 neutrinos. That'll determine for you very well the baryon density. That's the red dot dash line. The dash, the blue dash or cyan dashed line that's very broad is just BBN alone with the helium abundance. So on this scale, going from 5.5 to 7, it doesn't determine for you very well the baryon density. That's what this is telling you. Although deuterium does a lot better because of the steepness of that curve, you can get a much better handle on the baryon density just from deuterium alone. And then you can start combining BBN and CMB, as I said before, and then you can start combining it with the various observations, either BBN and observations alone or BBN and CMB and the observations. And so here's just a collection for getting what the mean baryon density is from using either BBN or CMB. You see that sort of in the middle, CMB and BBN already gets you to essentially the final result. So CMB, is great. CMB, BBN is almost all you need. The abundances on top of that essentially don't do very much in terms of determining the baryon density. All right, let's turn now to limits on particle properties if we allow the number of neutrino flavors to vary. So now we include n nu. Remember I said where this comes in is I said that the beginning of nucleosynthesis is determined by the freeze out when the weak interaction rates are equaling to the Hubble expansion rate. That weak interaction rate is going as GF squared T to the 5th. The Hubble rate is going as G Newton to the 1/2 times T squared, but it's really got the coefficient there of H. You see H squared is proportional to rho is proportional to the number of neutrino degrees of freedom. And so anything you change in this equation will affect nucleosynthesis. If you want to fill around with G Fermi or G Newton, although you should be careful about what you mean by that, you can do that and you can get constraints from nucleosynthesis. I won't talk about that. I'm going to restrict my attention to n nu here. This is the same plot that showed you before, now with blue is n nu equals to 2, the green is n nu equals to 3, and the red is n nu equals to 4. So helium-4 is quite sensitive to the number of degrees of freedom. Deuterium a little bit less so. And well, lithium is, but it's, again, we have the problems with lithium. Frequently people ask, what do you mean by a fraction of a neutrino? What does it mean? Because I'm going to give you a limit of n nu is less than, say, 3.2. What does the 0.2 mean? Well, certainly particles come in units of one, although you have to be careful because we're normalizing it to fermions. So a new scalar degree of freedom. So if you had a stable scalar, or stable on the time scale as nucleosynthesis, it would count as 4/7 of a neutrino. And so you can already get a 4/7. But you also have to be careful because we are assuming that neutrinos are at the same temperature, or all these new degrees of freedom are at the same temperature. They don't have to be. You could add new particle degrees of freedom at a different temperature. It could have decoupled earlier in the early universe. And so you have an extra little bit of freedom there, that if whatever new degree of freedom you're talking about has a smaller temperature than the neutrino temperature, and certainly than the photon temperature today, you can get any kind of non-integer result for delta n. Okay. So here's what happens if you allow that third degree of freedom, so baryon density helium and the number of neutrino flavors. Doesn't look a lot different. The thing that you might notice, if you if you have maybe a photographic memory a little bit, is the BBN predicted value for helium is now much broader. It's no longer that narrow line with that uncertainty of 0.0002. It's broader because we can get much wider distribution of helium abundances if we allow the number of neutrinos to vary. And so this is, again, using nucleosynthesis and the CMB. The others look fairly similar. And then you can plot the likely, this is again, CMB only determination of n nu and eta, which are the thin lines, and their values are shown here on the right, the same values I gave earlier. And the thicker lines are what happens when you combine BBN. So again, very good consistency. The best numbers are very close to 3, within 1 sigma of 3. And so it all looks quite good. I break it down a little bit here for you as to what the various element abundances do. Helium-4 does very nice on limiting the number of degrees of freedom, not so good on the baryon density, so left-right is sort of left open. Deuterium does sort of good on both. The closed lines are, of course, when you include CMB in both cases. And then if you include both helium and deuterium, you get the wide lines that look like that. And then when you add CMB, they all close up and give you a very, very consistent picture here. And these are, if you want, the numbers, depending on what things you're using in your likelihoods. You can skip down to the bottom, probably. That's the best set of numbers. Slightly different mean baryon density, but not that different. Best value for the number of neutrinos, 2.843. 2 sigma upper limit on that would be 3.15, or 3.2 if you want to just round it. There's a little bit of effect because of the new dp gamma rate. So the bottom line is now the top line, and this is what you would have gotten. Then we've also updated helium a little bit, what I've mentioned before. The theory value is, again, a little bit different. That's based on the Marucci rate, the Luna alone, and then our value, which is, again, very, very similar, almost identical to the Luna rate. And now it's a little bit closer to 3. I think it doesn't really mean anything. And again, within, it's now actually within 1 sigma of 3, but at the 2 sigma upper limit, or 95% upper limit, is 3.17. Now, and I'm almost done. I just want to give you a little bit of what we can expect from the future from just using the CMB. So CMB-S4, the next generation of CMB experiments, should get significantly improved values for helium-4 and for the number of neutrino flavors. So everything else being equal, of course, we don't know what they'll get, but if central values don't change, but the uncertainties drop to about 0.005, which is, according to the CMB-S4 study group, is reasonable. You see here that cyan curve, which was very broad on the left, which is the CMB only, turns into that dark blue. So it gets a lot better. Of course, now it looks a little bit discrepant, but that's assuming that the value doesn't change, which is no reason to expect that the value stays exactly the same. But barring any value that we know of, we just kept it to be the same value. So that's what you could expect. And that then gets compared with the observations and again, the BBN prediction, which is that very thin line. And then similarly, we should expect at CMBS4 to get determination of the number of neutrino degrees of freedom down to the level of 0.09, so significantly better than it is today. And this is what those curves would then look like. The upper one is the likelihoods from Planck, the existing likelihoods, again, based on these various combinations. Now the baryon density is marginalized, so this is a distribution only in the number of neutrino flavors. And then what happens if they get the same values with S4, and then you see again these CMB curves dramatically getting thinner, maybe even being able to test, I didn't mention it, the standard model value is not really 3 in the effective number of degrees of freedom for the CMB. It's actually 3.045 because there's some neutrinos, excess neutrinos left over from incomplete decouplings. It's just that E plus E minus annihilation also happens at about an MeV. And so saying that it's 3 is a little bit naive. The real number is 304. And that would be great if that could be tested by the CMB. But we're getting close to there. So I think I can summarize at this point. CMB and BBN, the two sort of foundations of Big Bang cosmology, I think at least with respect to deuterium and to some extent, to a large extent with respect to helium, are in great agreement. Lithium is problematic. I sort of glossed over some of those issues. It is high compared to the observations. And what that means, whether is that a signal of beyond the standard model of physics, or does it just mean that what's observed in these stars really isn't primordial? Well, we'll see. We don't have a definite answer for that. What I think is maybe on the horizon, which is certainly doable, is new cross-section measurements for DDN and DDP. That will further reduce, we'd like to get the theory uncertainty down to the level of the observations. The observations have done great with deuterium, almost unbelievably great at the level of this 0.03 times 10 to the minus 5. So we need to try and get theory to compete with those observations. For that, you need new cross-section measurements. And so Luna did a great job with DP gamma. Maybe we can get some new measurements on DDP and DDN. And then I think there's room for improvement on the helium, on the observational side for helium. So this is sort of the flip of the deuterium picture. Now we have great helium predictions, but our uncertainties in the observations are large. And I think there's some prospect that will be improved. All in all, standard model with 3 neutrinos, maybe it's boring, but it still looks good and it's nice to have some confirmation. Okay, I'll stop there.
Okay, thank you very much. We have some questions now. So Paul Davis, you were the first.
Yes, hello. That was a nice seminar. Thank you. I have a curious question. So from time to time, people say, well, how do we know that the photon has a strictly 0 mass? Maybe it's just very small. Well, if it was anything other than 0, you'd have 3 helicity states instead of 2. And back in the 1950s, there was a paper by Bass and Schrödinger showing that the extra helicity state, or classically that's a longitudinal polarization, would decouple from matter. So you wouldn't notice this with the Casimir effect or anything like that. But it would still be relevant to the Big Bang. You'd still fill those degrees of freedom, and it would contribute to the to the total background gravitational field. So my question is, can you use your analysis to put a constraint on the photon mass?
So I haven't thought about this specific question, but I think I can put it in terms of things that I have thought about. So if it really depends on, all you really care about is the contribution to the energy density at the time of BBN. So if it's really decoupled, and okay, this is the part that I haven't processed this to, at what point it would have decoupled from matter entirely. So
that depends on the mass, you see. That's the point.
So what you could use, you can use the existing constraints here that I've shown you. So in principle, that component, if it was really decoupled, would have a different temperature. Right. And so you can determine the temperature that it would, the maximum temperature that it would have to have, right? So it has to be a temperature lower than the photon temperature at the time of BBN. You have, it's 1 degree of freedom, so it's actually 4/7 of a neutrino. It's like a scalar in that sense. It's 1 degree of freedom, so it's like 4/7, and you would need to reduce that 4/7 to be on the order of about 0.2. So you would have to have the 4/7 times the ratio of the temperatures cubed to be less than about 0.2. So you can do the exercise, and that will tell you when it will have to have decoupled, because to get the temperature down, you would have to get to a decoupling temperature. Well, I don't know offhand, but
I didn't expect you to do the calculation.
Okay, good. I'm trying to do it in my head.
But I'd be interested to know, and then that can, of course, be compared with other observations to put a limit on the photon mass.
I imagine that it wouldn't be as good, but that's just a guess, because I would think that the experimental limits on the photon mass are going to be much more severe.
10 to the minus 50 grams is what.
Yeah, so although you have to put it, it'd be better to put it in GeV, but
of course. But notice that there's no
more. So it's very unlikely you're going to get a better limit from BBN.
In the graviton case, you don't have this problem. You get 5 helicity states instead of 2, but that leads to a discrete change in the perihelion precession observations. But there's nothing of that nature that you can do to rule out the 3rd helicity state for the photon. All you can do is
well, with the graviton, it would have decoupled at the Planck time.
Right. It's not an issue for you can't get at it from BBN.
Right.
But you might be able to get at the photon. So okay, I've taken up enough of your time.
Okay. Next question from Edward Chirek.
Hi, I'm not from this field really, but some years ago, a friend of mine, Victor Flambaum, put me into discussion of changing fundamental constants. That is what he was doing. And one of the constants was quark masses relative to QCD scale. And we find out that indeed BBN works so well that parameters of nuclear physics which enter into it are very well constrained. The most important parameter happened to be deuteron binding. So with small change of nuclear forces, you can move deuteron binding from 2.2 MeV to something else. And I don't want to mention the results we get, etc., but just to say that we play scenarios when, for example, deuteron binding is not 2 MeV, but 1. And it was vastly different abundances. For example, deuterium shoot up by nearly factor 1,000. Why? Because then there is much less time to BBN, etc., etc. So I just mentioned it for fun. And when I was describing it at the seminar, I remember Jerry Brown said, if deuterium abundance shoot up by 3 orders of magnitude, then all fishes in the sea will die.
That's probably true. No, I'm certainly familiar with your work with Flambaum. And it all grew out of, I think, initially out of the prospect that that the variations in the fine structure constant were very right. And so we started to look at that, and again for the point of view of BBN. And what we were doing a lot was looking at the variations of if you start varying some of the fundamental parameters, then it probably feeds into variations of everything else, including the quark masses. Basically, you're going to start varying things like Yukawa couplings. You could vary the Higgs Bev, all kinds of things they're going to start entering, but they're all correlated. So we tried to do something along that line. And this is several years ago, just showing that delta H over H is actually a variation of the Yukawa coupling, which would control the quark masses as well. That the binding energy, of course, feeds in there as well, although I don't show it explicitly here. But yeah, what I mentioned, what we were trying to do is get the lithium abundance down, right? But the problem is always that then the deuterium abundance is going up, even over this very, very limited range. And so, yeah, it's always nice and interesting to play these kind of games.
Okay, next question from Tanmay Rajaspati.
Hi, Keith.
Hi.
Very nice talk. I was wondering about the deuterium. Such good results, that such good observational results. Then can you test whether you have inhomogeneous BBN? Like if you look at the deuterium abundance in different directions, do you get different results?
It's a good question. Now, let me see if this, so that's the, let me just put that back up. Do you mean observationally? So there's.
Yeah, I mean, observationally, I mean, do you have the same deuterium abundance in all directions?
I don't know if I can answer. I'm not, it's a good question. There's not a lot of data. There's only 12 objects here. So I don't know what kind of distribution you're going to be able to build, over the sky for that. I also don't a priori know the directions of all of these absorption systems. It reminds me, the closest to that actually goes back to also some work by Flambaum on the variation of the fundamental constants, where they were trying to actually say that there was some correlation, some spatial correlation of the variations in the constants. And they're using these quasar absorption systems as well. So there is data out there that you can actually get their locations. I don't think so. I don't think you can do much with just 12 points, but
I see. I have just one follow-up. There was some talk some papers by Kure and Hirata talking about spectral lines in the CMB. Do you think that would help with the BBN, with the analysis of BBN?
Well, spectral lines of, if you're going to use it to try and get a better determination of helium-4, that of course would be impactful. Right, if you're going to get that directly from the CMB.
Right.
But just going back to inhomogeneous nucleosynthesis, so that was on, there's the inhomogeneity part on the observations, but you can also imagine doing inhomogeneous Big Bang nucleosynthesis, which was a big topic, in the 80s and 90s. The problem again with all of that, and this is a little bit points to the robustness of the standard model of nucleosynthesis, is that anytime you deviate, you start screwing things up, right? I mean, the problem is that the deuterium agrees so well that once you start deviating from this, you move away from that, and you try and improve something, but you mess up the deuterium much more. So
it's very
we
simple.
haven't looked at inhomogeneous nucleosynthesis in some time. We did in the past, but not recently.
Okay, thank you.
Okay, Next question from Sanjay Ray.
Hi, Keith. Thanks for that nice overview. I wonder whether...
Oops. Sanjay, we cannot hear you.
Sorry. Well, my mic, can you hear me now?
Yes, yeah.
Okay, thanks for a nice overview. I wonder if BBN can tell us something about lepton number asymmetry in the during the BBN epoch, and
well,
with lepton number.
Yeah, it certainly can. So that's another thing that is, well, has been looked at, and I think there are people that continue to still look at that from time to time. I think maybe most recently George Fuller's group has looked at that. So and I've done some work on that in the distant past as well. So I have a little bit of a theoretical bias against it, just because you need fairly large asymmetries, right? So you need basically asymmetries now getting close to order 1. And once we understood about baryon and lepton number violation in the electroweak theory, and so Svaleron effects, you basically expect the baryon asymmetry to be the same order of magnitude as the lepton asymmetry. And if we're talking about lepton asymmetries of order 10 to the minus 10, they won't have any effect. Now, I understand you can get around those arguments. You can do different things to still preserve a lepton asymmetry, but now you're doing 2 things. You're making the lepton asymmetry and you're somehow separating it off, sequestering it from the baryon asymmetry. But there are limits. You can ignore the origin and just say, okay, there is a lepton asymmetry. You can even play around with 3 separate lepton asymmetries, and people have done that. And in general, the muon and tau asymmetries, you don't distinguish, but you do distinguish both of those from the electron asymmetry, electron type asymmetry. And so you can look at what the abundances of the elements, how they change when you turn on those asymmetries. There were a lot more, there was a lot more freedom before these deuterium observations. And so like everything else, once you start deviating from the standard model, you're gonna have to do some extra work to maintain this agreement with deuterium. You have more room to play with helium-4. Maybe you say, maybe you're going to try and solve lithium, or maybe you're going to not worry about lithium, but you do have to worry about deuterium.
Thanks. So the basic point is that you need a very large asymmetry, and that's just ruled out by the deuterium abundances.
Well, again, we have BBN, would allow you to have, I'm just going to make up a number, but say 10 to the minus 4, which is still 10 to the 6 times bigger than the baryon asymmetry. I don't think nucleosynthesis would exclude a lepton asymmetry at the order of 10 to the minus 4. I mean, you have to get up around 10 to the minus 3 for, I think, the electron types. And again, this is out of memory. And maybe an order about 1/10 for the muon and tau type asymmetries. So you can get constraints on those asymmetries for sure from nucleosynthesis, but they're not going to be at the level of, once you're down below 10 to the minus 4, I don't think you're going to get any more from that.
Thanks.
Okay, there is one additional question in the chat. I'm not sure if you see it or I should read it for you.
I can't unless I stop sharing it.
It's fine. I'll read it for you. So the question is from Graziano Milato. He asks, the higher DP gamma to 3 helium-3 rates relative to the one used in FOYY causes the BBN likelihood function for D over H, shown in purple in the slide, might move to the left towards smaller values of D over H, or to the right. For what reason? So basically,
okay.
I hope you caught the question.
No, I think I got the question. So Whether I'm going to give you the right answer or not is a different question. So I think it's this. This is probably the figure that we're talking about, and whether you're going up and down. Now I guess you can see my arrow. I don't know.
Yes,
okay.
yes, because it's not full screen.
It's not full screen, so it's either this way or this way. It doesn't matter. The yellow, of course, isn't going to move at all. So the increased rate, well, I guess maybe it's as simple as that. There is a little bit of an increased rate, and you see it does push the BBN prediction down to slightly lower abundances. So, you know, we were a little bit to the right of the observations. Now we're a little bit to the left of the observations.
Okay.
Okay.
If it moved it a lot, right? So if you use the theory rate, then it would move it a lot. And now it's starting to look, you know, potentially discrepant. Again, it depends now on what error you assume for this. We were still giving it a fairly sizable uncertainty. If you think, you know the rate really well, you could make this purple one, you know, much narrower, and then you would have a bigger discrepancy. Okay, right now, as I said, the uncertainties have gotten a little bit smaller. I don't know if you can see it a little. It's probably hard to see that this purple is a little thinner than this purple. And the rest of the purple is due to the other cross sections, DDP and DDN.
Okay, thank you.
Okay, thanks. I don't see any other questions from the audience. I did have a sort of very naive question. In order to maybe resolve the problem with the abundance of lithium, is there perhaps some place in the universe where you might want to ideally detect that abundance so that you may get a clean result or something like that? Right now, as far as I understand, this is coming from the surface of some stars. Right. Is there perhaps some other place? I don't know, just to say it out of blue, interstellar medium or something else that might be cleaner in some sense?
Interstellar medium, not completely clear. You would have to, you know, again, go to something like absorption line spectra in really metal poor objects. I mean, you're getting it again in stars. You're again getting it from absorption, and you know, part of the problem is it's 10 to the minus 10, so the signal is very weak, and you know, once you start talking about cosmological distances, you just start losing because of the strength of the signal. It's a good question. I don't know if I have a great answer for it, but it would be really nice to have another way to get at the primordial abundance. You know, I should say, I mean, these people doing the modeling of these stellar, I don't know if I have any plots that they've made. That's helium, so it'd be a little bit after that. No, I think I don't have them for this purposes, unless they were farther down. Oh, yeah, I do have some. Maybe. Yeah, here's one. So this is some, I guess there's a couple. So this is even this better. So models of stellar depletion and turbulence. These are models by Korn, and there are other models. These people, you know, fight a little bit about themselves, but I guess that's true in any subject. Anybody too close to anybody else starts fighting. But you see the CMB abundance, and what they're claiming is that if they start with the CMB BBN abundance, that they get along this temperature range. So again, where you expect the plateau, their curve is the predicted abundance given a much higher BBN abundance. And so they're saying that, yeah, in this range, we do get something uniform and matching the data. You know, then people start saying, well, no, they don't really get it uniform and they miss things, and, you know, and then there's details, but the models improve. And so here's some models. This is from Fu et al. From a few years ago. Again, starting with the BBN abundance is what they start with. Then they get this red curve based on some of their models. Then again, why that model applies to all these stars with different parameters, it's not clear, but they are getting something that's pretty uniform, a very substantial, this is a log quantity here, remember. So this is a pretty substantial drop in the lithium abundance across all of these temperatures. So I don't know, maybe that's the reason.
I see. Well, thank you. I don't see any other questions from the audience. So using this moment, I would like to again thank you for a nice presentation, and thank you for taking time to prepare this.
Okay, well, thank you for listening.